So one of the main skills that we learn in algebra is how to analyze relationships between variables, where most of the time what's being referred to here is relationships between two or more variables in an equation or an inequality. And this is something we're going to be doing for the remainder of this entire course. Okay, and so as we've talked about in Chapter 2, one of the purposes of Chapter 2 is to get introduced to some of the basics of how we do this. Okay, and in the opening section, in the previous videos, we learned about one of the main tools that we use to analyze relationships between variables. That's the graph. We use graphs, which are created using coordinate systems. The fundamentals of a coordinate system is just related to mapping out locations and positions in actual 3D space. Well, in algebra, we take that construct and use it to visualize relationships between variables to where the variables don't necessarily have to have anything to do with actual 3D space. Okay, and so now what we're going to be looking at in this video, in this second section of Chapter 2, is, so we talked about how in pre-algebra and in Chapter 1, we've been putting different kinds of expressions and equations into categories, where the categories are based on the different types of terms that are in the expression or equation. Well, now with graphs, the fact that we can take any equation that has two or more variables and visualize it using a graph, with this, we're going to be putting different types of expressions or equations into even more categories, and with those categories being based off of if that expression or equation is associated with a specific type of graph, a specific shape of graph, etc. And so in this section, what we're going to do is we're going to look at a type of equation in two variables. So an equation in two variables, you can graph it in a 2D plane that results in its own unique type of graph, that graph being a circle. So what type of equation, what kind of different terms, what's the form of an equation in two variables to where all of the solutions to that equation are going to lie on some circle centered at some point in the Cartesian plane? Okay, so yeah, just note that we're in a Cartesian plane. So we want to think about what the equation of a circle in a Cartesian plane would be. However, we could do this same process for a polar coordinate system as well, and I'll show you what I mean as we do this. But as we've talked about, like the equation of a line in a Cartesian plane, it's not like if you want to have this and have a line in polar coordinates, you just switch the x to that. It doesn't work that way, right? Okay. So instead of just looking at what the equation of a circle is in a Cartesian plane, because obviously the textbook is just going to give it to us, we can go look it up. We should be able to develop it on our own. So okay, let's look here. Here's an XY coordinate system. And now we've got some circle centered at some arbitrary point, H and HK. H could be negative, K could be negative. HK is just any point. Okay, now let's think about what is, when we think back to geometry, what is the technical definition of a circle? What exactly is a circle? Well, it's the set of all points that are equidistant from a center point, with that distance being called the radius. Okay, so again, a circle is the set of all points that are the exact same distance from a center point, and that distance being the radius r. Okay, and so yeah, there's a circle, but like the center point is not on the circle. It's a very important reference point, but it's not on the circle, because the center point, the distance of the center point from the center point is 0. That's not, any point that's on the circle is the exact same distance from the center point, with that distance being r. All right, if we're trying to come up with an equation for not just this circle here, like any circle, as long as it's a circle somewhere in the Cartesian plane, we're trying to come up with an equation for that. What exactly is it that we're trying to do? Well, the whole idea is that, remember what this means. This graph here, what exactly does this mean? If there's an equation that represents this graph here, then the whole idea is that if you pick any point that's on this graph, that's going to have an XY coordinate, right? Any point. And then you plug that point into the equation, it's going to satisfy the equation. But if you pick any point in the entire Cartesian plane that's off the circle and you plug it into the equation, it's not going to satisfy the equation. And that includes the center, right? If you plug the center into this equation, it's not going to satisfy the equation. That's the idea. Okay, so with that in mind, how can we think about developing an equation that has the constraints that we need to make this happen? Well, we can think back to chapter 1. We worked a lot of word problems, and to where it was important to practice being given a word problem and then bringing that word problem to life in an algebraic equation form. So let's do that with the definition of a circle. So it's the set of all points that are equidistant from a center point, and we're saying that center point could be, it's arbitrary, HK. So like we what that means is that we can use HK in our equation, and those are just some constants, whatever you want them to be, some real numbers. Yeah, but they have to be real numbers because we're only thinking about graphs in this entire course with real numbers. So H and K are just some constants, you pick it. And then the equidistant from the center point, that distance is R. Okay, so we can use these three constants here. Now, how do we, that definition of a circle, the set of all points that are equidistant from a center point, how can we bring that to life in equation form? Okay, so they're equidistant from a center point. And we have the center point, HK. Well, okay, we just learned the how to calculate distances between points in the Cartesian plane. And that's what this is like. That's the inherent definition of a circle. In fact, it's actually kind of nice because this distance is constant. So yeah, let's try that. Let's say, okay, the idea is the distance between the center and any point on this circle, no matter what that point is. And so that would be any xy that you would plug into the equation that would satisfy the equation is going to be constant. Okay, so we're allowed to plug in any value in the entire Cartesian plane into the equation, but let's think about, okay, let's calculate the distance. How do we calculate the distance between HK and any point in the entire Cartesian plane? Well, all right. Well, HK would that's like x1, y1, and then xy. Then okay. So yeah, HK is, we've got. Let's do. So, all right. The distance formula is you've got any distance between 2 points in the Cartesian plane, x2 minus x1 squared plus y2 minus y1 squared, the principal square root of that. Okay, so, all right, we've got, you can pick any x point you want in the entire Cartesian plane, and you subtract that from h squared. Okay, now pick any y point you want in the entire Cartesian plane, subtract that from k squared. Now take the principal square root of that. Okay, now, so this is some distance between HK and any XY point that you pick. Well, okay, now we could make the left side whatever we want. We could make this some variable expression, whatever, but let's just make it a constant. And let's make that constant R. Well, there you go, boom. Now we've restricted the XY points that are going to satisfy the equation to be only these points that are an exact distance of R from the point H comma K. That's perfect. That's perfect. All right. So now let's clean this up a little bit. It'd be nice to get rid of this radical. So let's square both sides. Okay, and that's going to result in, let's do x minus h squared plus y minus k squared is equal to r squared. And there we go. This is, you can pick any center point you want, h comma k, in the entire Cartesian plane. And then you can pick any radius you want, r. And then if you put that into a form like this, just so if you had like center point 2, 3, we'll just substitute. You have x minus 2 squared plus y minus 3 squared. And if you wanted a radius 4, then 4 squared is 16. And there you go. That's the equation for the circle centered at 2, 3 with radius 4. Or if you made this minus 2, it would be x plus h squared plus y minus 3 squared is equal to 16. All right, great. There you go. And yes, this is the standard form right here. This is the standard form for the equation of a circle. Now, notice, though, that so the h and the k can be any point in the entire, as long as it's like each coordinate is a real number, it can be any point you want. But it would make no sense to say that, to specify a negative radius. Why is that? If I said, okay, I've got a circle centered at 3 minus 5 with radius minus 16. Well, no, because how is that? Think about how we developed this. We developed this equation using the distance formula, which means that what comes out of the distance formula, it's coming out of this principal root. It's always a positive number, no matter what. So a negative radius wouldn't make sense. Yes, if you plugged in a negative radius into this equation and you squared it, you get a positive number. You could still go graph the circle. Okay, like if I said minus 4 and I plugged all of this in, I'd still get an equation of a circle and it would work. But you'll see later in this video what I mean about how you can't really think about the idea of a negative radius here. Okay, now also note that if r is equal to 0, then you don't have a circle. So if r is not equal to 0, if this is some, r is some positive number, and so you get r squared as some non-zero number. If you plug in h and k, that's not on the circle. You get 0 squared plus 0 squared is equal to some positive number. That doesn't satisfy the equation. The center is not on the circle, except for the case where r is equal to 0. Well, but then that's not a circle anyway. If r is equal to 0, then this equation just represents a point. Okay, but now what if we wanted to develop an equation for a circle in a plane that is mapped out with polar coordinates? Could we do that? Well, okay, let's just make sure we're perfectly clear on exactly what this question is. The question is that, so you've got some plane, this two-dimensional plane, okay, and inside the plane there's a circle. But we can choose to, as far as locating all points in this plane, we can choose any coordinate system we want. If we think about at the center of the plane would be the origin of whatever coordinate system we choose, we could put a Cartesian coordinate system. We could put a polar coordinate system. So there would be the radiuses, and then you'd measure, there would be your angles. We could put any kind of coordinate system we want. But the idea is the circle is not going to change. Like, no matter what the coordinate system is, the question is, what equation in whatever coordinate system would be such that any point on a circle centered wherever in the plane would be a solution to that equation, and any point off the circle wouldn't be a solution. Okay, and so again, as we've talked about, you can't just think about that. So in the Cartesian coordinate system, in a plane, you have the x-y pair. The two dimensions are x and y. In a polar coordinate system, you have r and theta. You can't just come here and replace x with r and y with theta, and now that's going to be, if you had a polar coordinate system for a plane, all the points that satisfy that equation are going to be a circle. No, that's not going to work. Now, there are ways that you can, like conversions you can use to convert from rectangular to polar or vice versa, to where we could just say that, for example, x is equal to r cosine theta, y is equal to r sine theta, plug this in for x and y, and then, we'd have to change, these two r's would be different. This is the radius of the circle. This is like the r in the actual coordinate system. But plug this in and then simplify, and that would be, what would result would be the equation for an actual circle anywhere in the plane, but with the plane being mapped out with polar coordinates. But if we wanted to develop this actually from scratch with a polar coordinate system, just like we did here in rectangular, well, we just need to use the distance formula for polar coordinates. Right, we talked about you can come up with a distance formula, which is the distance between any 2 points in a plane, where we came up with that distance formula for the Cartesian coordinate system. But you can come up with a distance formula with any coordinate system, and for the polar coordinate system, that's d is equal to the principal square root of r1 squared plus r2 squared minus 2 r1 times r2 cosine of theta 2 minus theta 1. So we could just do the exact same thing. We could say, that r1 and r2, that this r is the radius of the circle. This is the coordinates, but it's r theta. So the first point has coordinates r1 theta 1. The second point has coordinates r2 theta 2. We could do the same exact idea. And setting this equal to, if the radius of the circle was capital R, let's say, we'd set this equal to capital R. R1 and theta 1 would be the center of the circle, and then R2 and theta 2 we would just set to be R and theta. You see? So the standard form of an equation of a circle. Given a circle centered at HK with radius R, the standard form of an equation of the circle, also called the center radius form, is given by, and there it is, where R is greater than 0, which that might be confusing you a little bit, because it's like, well, we could input a negative R and that would still work here. But yeah, it would only work because that would be if you inputted R is equal to -4, well, -4 squared is 16. That would be implying that the radius is 4. And so you might be thinking, well, okay, but then why not, you could input a -4 for R or a 4, and you'd have the same radius of 4. Well, no, we'll see later in this section why we're not allowing for the idea of a negative radius here with the equation of a circle. But okay, so now let's look at this example. It says, write the standard form of an equation of the circle with center at -4, 6, and radius 2. So the standard form, x minus h squared plus y minus k squared is equal to r squared. So, okay, a circle that's centered at -4, 6, and has radius 2. Well, okay, -4, 6, that's the center. That's h comma k. It's really important that you get good at substituting values into equations or pulling values out of equations. It's really important, like equations like this, these like standard forms of equations, because you don't want to say, okay, h is -4, x minus 4 squared. No. This is, you do x minus, then you get to h. Now substitute what h is. Okay? Y minus, you get to k. Now substitute what k is. You get to r. Substitute what r is. Right? So like whatever r happens to be, all of that is getting squared. All of it. So we're not allowed to have negative radiuses, but if, just hypothetically, if r was -3, all of r is getting squared. All of it. Okay, but so now with this, let's just simplify. So x minus -4 is x plus 4, y minus 6, and there we go. There's the equation of a circle centered at -4, 6 with radius 2 in the Cartesian plane. Okay, now if we were going in reverse and we were looking at an equation like this and thinking about, let's pull out what the center, if we were asked, what's the center of this circle and the radius of this circle? Well, okay, you have to compare it to the standard form. The standard form is x minus h. So okay, y minus k here. So if k has a minus, if this has a minus in front of it, well, then just pull out it's 6. It's not -6, it's just 6, because this already has a minus in front of it. You see? And since this has a minus, but we have a positive 4 here, well, that must be, that means that this is -4. Okay, let's look at this next example. Write the standard form of an equation of the circle with endpoints of diameter located here. So the diameter runs through the center of a circle. So the only information we're given about this circle is that 2 endpoints of a diameter are located at these points in the Cartesian plane. And now we want to write the equation of this circle in standard form. So, okay. Well, we know that the center of the circle is going to be at the midpoint of this diameter. So, yeah, we know how to get the coordinates of the midpoint between 2 points, and so we can get the coordinates of the center of the circle. So what we do is we just add up the 2 x coordinates and divide it by 2, and then add up the 2 y coordinates and divide it by 2. So the order doesn't matter. So 3 plus -1 is 2. Divide that by 2. That's 1. That's the x coordinate of the center. Okay, add up the y coordinates. 4 plus 0. Now divide that by 2. So 4 divided by 2 is 2. So there's the center. The center of the circle is at 1, 2. Okay, but now we need, with that standard form, so we have h and k, but to write this out, we need r. How do we get r? Well, we've got the center of the circle in 2 points on the circle, so we can just use the distance formula to get the distance between either of those 2 points. So the radius is going to be, we just do, so x2 minus x1 squared. It doesn't matter which point we pick to be point 1 or point 2. So 1 minus -1. 1 minus -1 is 2. And we square that. Okay, now 2 minus 0 is 2, and we square that. So this is going to be, let's see, 4 plus 4, we have the square root of 8. Okay, so now we have the center and the radius. So x minus +1 squared plus y minus +2 squared. And now the square root of 8 squared is 8. There we go. This is the equation of a circle that has endpoints of one of its diameters at the points -1, 0 and 3, 4. Okay, now the general form of an equation of a circle. We just looked at the standard form. Now we want to look at the general form. So what are they talking about here? Well, as we look at different types of equations with different types of graphs, what you're going to see is that there's 2 different types of forms that you'll see equations in. They'll either be in like an organized, factored type of form, or maybe not always factored, but just some sort of organized form that allows you to read off features of that equation's graph straight from the equation. Like, for example, what we were just working with the equation of a circle. We could read off straight from this equation what the center of the circle is, what the radius of the circle is. Okay, and we're going to see with other types of graphs that there's more than one type of like organized form like this. There's different, like with a line, for example, you have the slope-intercept form, you have the point-slope form. There's 2 separate forms that allow you to read off features of that graph straight from that equation. Okay, but now there's another type of form that you can put equations like this in. So we could take this equation here for a circle, this organized form, descriptive form, and put it into another form that's called the general form. And this form can actually be really useful as well. So all the general form is for any type of equation with any type of graph is you're just expanding everything out, completely expanding everything out, bringing everything to one side with the other side of the equation equal to 0, and then like combining like terms and then just putting everything in a descending or ascending order of the exponents. Okay, so for example, let's do that here. If we expand out x minus h squared, what do we get? X squared minus hx is minus 2hx. Minus h times minus h is h squared. Okay, now we've got y squared minus ky is minus 2ky plus k squared is equal to r squared. Okay, now let's just bring everything to one side and kind of group similar terms together. So let's put the x squared and the y squared term right next to each other. Now let's do, okay, minus 2hx minus 2ky. Let's the x to the first and the y to the first term. Now let's bring the terms that don't contain a x or a y together. So plus h squared plus k squared minus r squared is equal to 0. Okay, now what you can think about, though, is that if we actually had this all expanded out and there were actual values, we had actual values for these constants, the h and the k and the r. Well, what this would look like is we'd have x squared plus y squared, and then 2h is going to be some arbitrary constant. I'll put plus a, but it could be negative. H could be positive or negative, whatever. So plus ax, and then plus by, and then h squared plus k squared minus r squared is just another arbitrary constant. So in the completely expanded out form of a circle, the equation of a circle, this is what you're going to see. X squared plus y squared plus some constant times x plus some constant times y plus a constant is equal to 0. This is the general form for the equation of a circle in a plane. But like by definition, a circle is the geometrical definition of a circle. It's contained in a plane, so every circle is planar. So I mean, this is the general form for the equation of a circle. And this is the general form for any kind of equation of anything is going to be like this. Just expanded out, everything brought to one side, like terms combined, and put in like a, an organized order like this to where you can clearly see the different terms that you have with their coefficients. And general forms can actually be really useful because it gives you a sense of the bare bones types of terms that you have for that type of graph. Okay, so like what's unique about this is that you might look at this and say, well, couldn't we put any quadratic equation in two variables into a form like this? Well, no, not necessarily. I mean, because look, the coefficients on both the x squared and the y squared they both need to be 1. Well, that's not necessarily going to always be the case. Yeah, you can make one of them equal to 1 if you want with no problem, but then the other one also has to be equal to 1. Okay, now, so if you were presented with some random equation with all kind of stuff jumbled together and you didn't know what it was, but you were familiar with the general form of the equation of a circle and you recognized that these terms look like they might be related to a circle, and so you put it into you brought everything to one side, cleared the fractions, combined like terms, etc., and you saw that you do in fact have a circle. You do have an equation of a circle. How can we go from the general form to the standard form? So, okay, for example, if we had, so x squared plus y squared plus 10x minus 6y plus 25 is equal to 0. How could we convert this into the standard form? Well, what we're going to need to use is completing the square. Because remember, when we complete the square, the result of completing the square is we get something like this. Well, that's exactly what we're looking for to get to that standard form. So what we can do is we can we can bring these, so you have x squared plus 10x. Now, leave a space here. And then we've got y squared minus 6y. Leave a space here. And let's subtract 25 from both sides. 0 minus 25 is minus 25. Okay, now let's create perfect square trinomials here and here. All right, so we've got, let's see, expanding a general perfect square trinomial, you have x squared plus 2ax plus a squared. So, okay, to create one from this x squared plus 10x, we see that 2a is, in that case, is equal to 10. So a is equal to 5. So a squared is 25. But now we don't want to change the equation, so let's add 25 over here. All right. Now let's do the same thing for the y expression. So in that case, we see that 2a is equal to minus 6. And so a is minus 3. Minus 3 squared is 9. Let's add 9 to both sides. And there we go. So now we can turn this x squared plus 10x plus 25 into x plus 5 squared. And we can turn the y squared minus 6y plus 9 into y minus 3 squared. And that's going to be equal to minus 25 plus 25 is 0 plus 9. And there we go. This is a circle centered at negative 5, 3. The center is at negative 5, 3. And the radius is 3. Okay, great. Now we're going to talk about something that's going to explain why, with the standard form here of the equation of a circle, why the r can't be negative. Why can't this r be negative? So, the general form here, this general form for the equation of a circle, the majority of the time, if you have an equation like this, the majority of the time that does represent a circle, but sometimes it doesn't. So if we think about, if we're starting with an equation in the general form like this, and we want to convert it to the standard form like we just did. So we did that with this equation here. In general, what you get is, when you go through the whole completing the square process, what you get is, so you force the x to have an x plus or minus a constant squared, and plus y plus or minus a constant squared. So you force this to match up well. Okay, but on the right, what you end up with is just some constant. That's what we got here. We ended up getting, on the right, we got positive 9. And so in general, anytime you start off with a general form like this of an equation of a circle, you're going to complete the square, get the sum of these two squared terms, and then on the right, you're going to end up with a constant. Now, in complete general, if for all the different types of general forms that you could possibly come up with, the general forms of the equation of a circle, sometimes c is going to be 0, and sometimes it's going to be negative. And then obviously sometimes it will also be positive. And if it's positive, greater than 0, then you do have a circle. This is the equation for a circle because this matches up perfectly with the standard form. But what about if c is 0 or negative? Well, if c is negative, then if we examine this side here, you have the sum of two squares. Well, like, it doesn't matter what x is or what h is. When you square it, it's going to be positive or at the lowest 0. And the same thing here. So there's no way this side on the left can be anything less than 0. And so as far as if we're just thinking about real numbers, which in regards to plotting a circle in a plane, we're only thinking about real numbers, there is no solution to this equation if c is negative. So obviously there's no circle there. And that's why when you think about the standard form of the equation of a circle, your r is not allowed to be negative. Even though, yes, if you said r was negative 4 and you plugged it in here, then you'd get a valid equation. But what's underlying that would be the assumption you'd be assuming this. You'd be implying this, that C was -4. If you said R was -4, you'd be implying that, okay, you have an equation like this, where C is -4, and there is no solution to that equation, no real solution. But then furthermore, it's not a circle, right? It's definitely not a circle, at least in a Cartesian plane when we're just plotting real numbers on the X and Y axes. Okay, now, but what about if C is 0? Is that a circle? Does that have is there no solutions to that equation as well? Well, no, if C is 0, there's actually only one solution. The solution is when X is, the XY is the center point. X is equal to H, Y is equal to K. Because if C is 0, if you plug in X is equal to H and Y is equal to K, you get 0 squared plus 0 squared. 0 is equal to 0. But any other point, it's not a solution. And so, but that's fine, but that's not a circle. That's just a point. So if C is equal to 0, you don't have a circle in a plane. You just have one point. And so that's another reason why R can't be 0, because this is the standard form for the equation of a circle. If R is equal to 0, that's not a circle. I mean, I guess if you want to be really technical, it's a circle of radius 0, but technically, no, that's not a circle. Okay, now, but if C is greater than 0, then the radius is equal to the principal square root of C, the positive square root of C. And this is a circle if C is positive. So, okay, now, what if you do have one of these cases where it's like the general form of an equation of a circle, or, even the standard form of an equation of a circle with R being 0, or like, it's like, or R being negative, then you don't have a circle, and these are called degenerate cases. Okay. So here's those three cases that I just summarized, the different C values. All right, now here's an example. Let's take this general form and put this into standard form and see, do we have a circle or is it a degenerate case? So you have x squared plus y squared minus 14y plus 49 is equal to 0. So yes, this is the general form. So the general form is x squared plus y squared plus ax plus by plus c is equal to 0. Well, a, b, and c could be any real number. They could be 0. In this case, a is equal to 0. Okay, so, but let's see. We've got x squared plus y squared minus 14y plus, and let's leave a space, subtract 49 from both sides. Okay, so with if you have y plus a squared, that's y squared plus 2ay plus a squared. So in this case, 2a is equal to minus 14, so a is equal to minus 7. Minus 7 squared is 49, so let's add 49 here and add 49 here. So we have a perfect square trinomial here. So you have x squared plus, and then y and a is minus 7. Y minus 7 squared minus 49 plus 49 is 0. So we would, hypothetically, we would be thinking that this would be a circle with the center at x coordinate 0 and y coordinate 7. So HK would be 0, 7. Okay, but the C value is 0. So it's like the radius is 0. That's not a circle. This is a degenerate case. There's only one solution to this equation. Like if we plotted this equation in the Cartesian plane, we would have 1, 2, 3, 4, 5, 6, 7. That's it. That's the entire equation. It's one point. That's not a circle.